Good afternoon, everyone. Welcome to week 3 live session on structural analysis part 1. It's an elementary course in the analysis of determinate and indeterminate structures. Today is week 3 and all are you welcome here. And I hope you people are clearly hearing my voice and presentation is also visible. This is the third week, and in last 2 weeks, we started with the introduction of the structural analysis and why it is important, and then we moved on to determination of loads, types of loads, and analysis of structures by finding the support reactions. And moving forward in the same direction, today we are having first basic types of structures that we find in structural analysis is plane and space trusses. So, what actually is a truss? Truss is an assemblage of straight members. So we have straight axial members. Those members are assembled in such a way that all their connections are flexible and they form a rigid configuration. What happens because of their lightweight and high strength? Because of their lightweight and high strength, uh, because of their lightweight and high strength, trusses are widely used. They have a very widely used applications in supporting from bridges, roofs of buildings to being used as support structures in space stations. Okay, hope this point is clear to you. In the figure, we can see that we have a truss, which is a supporting structure for our roof. Okay, here is our roof, and for that we have a supporting structure truss. And this, I will zoom it out. In this, we can see that different members like this one and this one are connected by flexible joints. Okay, flexible joints here, and this, for example, this is simple truss one, triangular, and this truss is connected to other members to form compound trusses. I will tell you all these definitions one by one once we go ahead in this lecture, in this session. So, as I already told you that for structure analysis, we make some of the assumptions to make the analysis simpler. But those assumptions are not actually fully valid in practical situations. But while designing these structures, we try to take care of all these assumptions so that our structural analysis methods and structural analysis calculations for the designs are valid. So taking up to the analysis part, what are the assumptions for the analysis of trusses is that all the members are connected at their ends. These members are connected at their ends by hinges so that there is no friction between different members. And in case of plain trusses, if there is a space truss, what I mean by plain truss is, for example, I have a truss like this. It's in 2D. Okay, it's a 2D truss in xy plane only, so I call it a 2D truss. Okay, so if the same truss, triangular truss, but it has members in all three directions, all three respective coordinate directions, so I will call it as a 3D truss, like this. Okay, it has like this. We have the coordinate system x, y, and z system. Okay, for example, it is supported like this, it is supported like this, it is supported like this. Okay, I called it a 3D truss. So in 2D truss we have flexible, sorry, we have flexible hinges, flex hinges. Okay, in 3D truss we have ball and socket joints. Okay, you people will be well aware of these terms, flexible joint and ball and socket joint. Okay, then what is the second assumption is that it's one of the main assumptions that makes that these trust structures unique. all loads and support reactions are applied at joints only. Okay, so at the joints of these members, for example, this is a roof truss, the load will be applied only at the joint, neither not at any member location. For example, p load. Okay, so it will be applied at joints only. There is a very big reason behind this. I will tell you that. What happens in a trust member is that we assume that in, for example, this is a trust member. We assume that in trust member it transfers loads through axial compression or axial tension only. Okay, P. So it is joined at this joint point. This is joined at this joint point. So for example, let's take an example. This P load was not applied at the joint point. It was applied at somewhere in between, in middle of this member. So you know that if this load was applied at here, it would cause bending in this structure. Okay, and this bending will, we will not tolerate this bending in these small sized structures. Okay, that's why it's important we apply the loads only at the joints of the these structures. And another third important assumption is the centroidal axis of each member coincides with the connecting coincides with the line connecting the centers of adjacent joints. For example, I have this one. I have two members like this. Sorry. I have two members like this. I have one member like this, another member like this. Another member like this. So their centroidal axis will be somewhat like this. It will be passing. This will be centroidal axis for this one. This will be centroidal axis for this one. Okay. Member one, member two. Centroidal axis for this one. Okay. So let us call this centroidal axis C1, centroidal axis C2. This is member one, member two. What the assumption says that the centroidal axis of each member coincides with the line connecting the centers of adjacent joints. So I have another one. So for example, I have one more truss member here. So this assumption states that these members are connected at a joint like this, that their centroidal axes coincide at the joint point. Okay, so I will make it to intersect here. It is centroidal axis C3 for member M3. It is centroidal axis C3 for member M3. So you people are looking at this point. So this is a joint here. Okay, you people look how beautifully this is being getting intersected joint here. Okay, this, that is the basic point of this assumption, that the centroidal axis of all the members intersect or coincide intersect at the joint. Okay, so what happens is that the load transfer is through axial tension and axial compression only because of this assumption. So I will write here what is this. Is this, this is assumption. This is assumption 3 that we studied. Okay, then moving forward, so I just made you familiar with three different types of assumptions that are used for the analysis of trusses. Then there are different types of truss structures that have been studied in that are commonly used for bridges, but these can be used even for structures and for roofs also, roof supporting structures. So this is this, for example, pad truss we are having, and we are having Warren truss, we are having Parker truss, we are having K truss, K type truss, we are having Baltimore truss. Okay, so we will be solving the examples regarding these trusses also. Few examples we will solve. Okay, hope this is clear to you guys. Then I want to focus here on what type of forces are getting transferred through a truss member. For example, we are having a truss member like this. This is a truss member here. Okay. So, for example, it is acting by load FA and FB. So, this FA and FB will be resolved in such a way that truss member will take it through only either tension, either tension, either tension, or it will take it through compression only. Okay, it will take it through compression only. Compression only. Okay. Then the next thing is arrangement of members of a plane truss and internal stability. So look, a truss, one of the simple trusses that can be constructed is using three members like this: one, two, and three members, and then connecting them together. Okay. So this is the simplest type of truss that we can connect using three members. But there is a particular way of connecting these members such that the structure that we form is then stable. For example, if I connect these three, instead of these three members, I will connect four members. One member, two member, three member, four member. I am encircling those so that it will be easy for you to recognize this is a member number. Okay. But if I look at this structure, if I apply loads like this, shear loads like this, these are not actually the shear loads, actual loads at the joints only. So you will see that it will skid like this, it will deform like this. It's not an internally stable structure. It is because of some of the reasons I will tell you in a couple of minutes. But look, we are having four members here. We are having four members here. Still, it is unstable here. Okay, unstable here. And but I am having only three members here, but it is stable here. So what is the thumb rule is that how can we obtain internally stable structure, internally stable trusses that using a simple truss, that's a three-member truss which is stable as it's already stable, we connect members to it. We can connect a different members to it to make a larger truss structure. So here the same is written here. A simple truss is formed by enlarging the basic truss element. Basic truss element is triangular element, which contains three members and three joints. Three members and three joints are there. Okay, by adding two additional members for each additional joint. Okay, so the total number of members is m. A simple truss is given by. Okay, for example, simple truss is like this. It is having three members and three joints. So in 2D, I can connect two more members to here. Okay, one member and another member. Okay, and sorry, and to another joint, I can connect to two more members. To each joint, I can connect to two members like this. Okay, two members. So for example, this was joint one. This is joint two. This is joint three, and connected new members are one, two, three, four, five, six. Okay. So, what will be the total number of members in this stress? As already it was having three members, and I connected more members to three joints. Okay. two members, three joints. Okay, let me do the calculation. So it will be already there were three members, and to each joint I deducted. Total number of joints that are now coming in our new structure is J. Let it be J, and total number of members now will be M. So already there were three members. So keeping them, taking them into account, J is the number of new joints, but there were already three joints already. So J minus three will be the total number of joints in that structure. So each joint is getting two members. So two times number of joints, two times number of joints plus three, already it comes to J minus three. Okay. So M is equal to M equals 2J minus 3 is an equation which relates number of members M to the number of joints J in an internally stable truss. Okay. Hope this is correct to you people. So what I was telling you that this is a simple plain truss one. To it we add two new members like new joint. We formed a new joint one here. Like this one, we formed a new joint here, and continuing the same process, we get a different truss structure. Okay. Hope this is clear to you. A compound truss is another type of truss structure is compound truss. Okay. So, what is the definition of a compound truss? Compound trusses are constructed by connecting two or more simple trusses in to form a single rigid body. To prevent any relative movements between the simple trusses, each must be connected. Each truss must be connected to the others by means of connections capable of transmitting at least three force components, all of which are neither parallel nor concurrent. Okay, so here you people can see that what is a compound truss here like this. These are compound trusses. Compound truss, definition of a compound truss. Then we will talk about the internal stability, like we talked about internal stability of our did for determining the static indeterminacy. We talked about internal stability. So I told you that this equation represents number of members to the number of joints. So here in this structure, let me make one thing clear. One more page I will add. So I told you this four member structure is. So I told you this four member truss is unstable. I will tell you why. So number of members M we can count. M is equal to four in it, and number of joints J is equal to four. So let us calculate our as per our equation. M is equal to 2J minus 3 is stable, but here, yeah, 2J minus 3 equals 2 times 4 minus 3. 2 4 the 8 minus 3 equals 5. So M is less than 2J minus 3. So M is only 4, and we have this 2J minus 3 as 5. So there is a lack of one member. So members are lacked by one unit. So if there was one more member like this one more member, let me draw a different color. If there was one member here, only one member more, or like this one member more, this truss would have been internally stable truss. Okay, so that is the case here written here. If M is less than 2J minus 3, the truss is internally unstable. Okay, the truss is unstable. If M is greater than or equal to J minus 3, the truss is internally stable. I told you that for triangular truss, we have M equals 3, J equals 3, and we got 2J minus 3 equals 2 times 3 minus 3 equals 3. So our m is equal to j minus 3, so it is stable. Okay, that's the case here. Same you will get in other type of structures. So we will do the same exercise here. I have given some problems. Classify each of the plane trusses shown as internally stable or unstable structures. So first is a Howard truss. Like this, we can calculate the number of members in it. Let me enlarge it a little bit. Okay, so what is the number of members? Number of members is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. We have 20 number of members. M is equal to 20. J is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. J is equal to 12. Okay. So if we will calculate it, M is less than 2J minus 3. M comes out to be less than 2J minus 3. So it's an internally unstable structure. Okay. And internally unstable truss. It's an internally unstable truss. Then coming to another point, another truss. If you see, it has number of members 26, number of joint is 15. Again, M is less than 2J minus 3. It's internally unstable. Okay. If we look at this type of truss, M is equal to 25, J is equal to 12. So M is coming out greater than 2J minus 3. So it's internally stable. Okay. Hope you people are getting my point. So then next is static determination, indeterminacy, and instability of a plane truss. Continuing with the plane truss only is that we consider a truss to be statically determinate. One second, someone wants to join. Statically determinate if the forces of all its members as well as all the external reactions can be determined by using the equations of equilibrium. The condition of static instability, determinacy, and indeterminacy of plane truss can be summarized as follows: M plus R less than 2J, M plus R is equal to J, M plus R is greater than 2J. Okay, so these are the conditions where R is the number of reactions. Okay, to be calculated. So
Excuse
I
me,
will,
sir.
yes.
Sir, can we use this condition that m should be to be internally stable, m should be greater than 2j minus 3? Is it only applicable on trusses, or can we use in other frame structure also to check the internal stability?
In frames, I'm coming to frames. In frames, we can also use the same thing, but there can be sometimes some additional things like we have hinges in there, so we have to consider those things also in that one. But
Okay, sir.
in frame structure, so here we come. Here we have only for example, we have two equations like this along x and y. 2D along we write fx is equal to 0, fy equals 0, summation fx equals 0, summation fy equals 0 in trusses. But we have additional equation in this. I mean to say that this one frame structure, we have summation m Z is equal to 0 because frames are capable of taking bending moment also. So their changes, the equation changes a little bit, but the concept is somewhat same. Hope you got my point.
Yes, sir.
Yeah, I will come to that also. Maybe in the next lecture that comes. Okay.
Okay, sir.
So this is m plus r is less than, if m plus r is less than 2j, it is a statically unstable structure. Okay, and if m plus r is equal to 2j, it's statically determinate class. So we can compute all the reactions with the help of given equilibrium equation, that is summation fx is equal to 0, summation fy is equal to 0. Okay, for and if m plus r is greater than 2j, statically indeterminate class. So that what happens is that we cannot compute the internal forces, that is the actual force, either compression or tension, either compression or tension, we will not be able to compute in certain members. That will be the static indeterminacy of that structure. Okay, so our basic formula is m is equal to 2j minus 3. It is stability equation, stable stable equation. So at each joint, j is, if j is the number of joint, we can write 2j is number of equations we write. Okay, we can write. So this point is clear to you, because if we have j number of joints, we can write 2j equations. What are the equations? Summation fx equals 0, comma summation fy equals 0. Number of equations we can write this thing. So this is for the internal structure. So for the external structure, if r is the number of one more thing, for external structure we can write three equilibrium equations. Okay, number of equilibrium equations, number of external, sorry, number of external equilibrium equation. So we can write three equations, that is summation fx equals 0, summation fy equals 0. Keep that, bear that in mind that I'm only talking about plane trusses, and we don't have space trusses here. Summation mz equals 0. So now here comes a point. You people should ask me that you were telling that there is no moment. How you are writing summation mz is equal to 0? But please note that I'm writing it as a number of external equation in truss member, not internal. Internally, I wrote only fx equals 0, fy is equal to 0, because there are only axial forces and no bending moment. But if I consider external joints, either it be hinge joint or it be roller joint, I can write summation of mz equals 0 for these types of joints. But internal joints, that's the truss joints, I cannot write mz is equal to 0 because there is no moment. They cannot take at any moment at all. But these things can take the moment now, that is m z is equal to summation of mz is equal to 0. So total number of equations, let me add one more, this is very important for you people. So total number of equations that I can write is number of equation we can write for truss member, for truss is I write it as neta E. Number of equations is 2j for j number of joints plus 3 external equations. Okay, this is any. Okay, then coming forward, suppose R is equal number of external reactions to be determined. Okay, and number of internal forces that are to be determined is because as we all already know, for each member there will be either tension or there will be compression. So for each member there is one unknown, that is unknown for, force member force, and for m members it will be m is equal to number of external, sorry, it's not number of internal reactions, not reactions, it is number of internal forces to be determined. So, as I already told you in the previous lecture, is a determinate structure is that structure in which number of unknowns, that is where I wrote is number of unknowns is equal to ne. We can determine it as is number of unknowns we can determine by number of equations. So we have that equation there. Okay, so if my m plus r is equal to 2j plus 3. Okay, this one. Then here we see that classify each of the plane truss shown in the figure as stable, unstable, statically determinate, or statically indeterminate truss. Okay, so in the first truss we can see that the number of members m is equal to 17 and number of joints j is equal to 10, and reaction forces to be determined are is equal to 3, because we can have one reaction, this hinge joint, we can have two reactions, and we can have one vertical for roller. Okay, so if we compute this m plus r is equal to 20, and j 2j is equal to 20. So m plus r is equal to j is statically determinate. Okay, and another same structure. Okay, no, same structure is m17 j10 r is equal to 2. So it's not the same, it's a different one. 1 2 3 4 1 2 3. Okay, here m is equal to 17, j equals 10, and reactions r is equal to 2, because it is this one and this is this one. Okay, so if we see that m plus r is less than 2j, it is unstable because it can roll down like this. Now if I give the force, it will move like this one, so it is unstable. This type of structure, it has m equal 21, j equals 10, and r reaction force is 3. Reaction forces are this and this. Okay, so if I can calculate m plus r, it is coming much greater than 2j, so it is statically indeterminate with indeterminacy I equals 4. Okay, so there will be four member forces, which we will not be able to determine by static equations. In the same manner, you can calculate this thing. Okay, Now, one more we can check here is it is having three reactions at previous one, this one, and this one. M is equal to 16. These are 16 members. I can count for you 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 members. Number of joints is J is equal to 10, and reaction forces are 3. M plus R is less than 2J, so it's unstable. Okay. Firstly, it's an unstable structure. Then this can be statically determined. Look here, M is equal to 26, J is equal to 15, R is equal to number of reactions is 4. So here is 1, 2, 3, 4. Okay, it M plus R is exactly equal to J, so it's statically determinate. All the four reaction forces we can compute, and all the 26 member forces we can compute using writing equations of motion, equations of equilibrium. Now there comes the analysis of plane trusses by the method of joints. So now we have to analyze these structures to compute the reaction forces and also internal forces in all the members. For that we have two methods: method of joints and method of sections. I will go one by one in all the three method of joints and method of sections. In method of joints, I have written here is that the axial forces in the members of a statically determinate truss are determined by considering the equilibrium of its joints. So, as by the name it suggests, it is analyzing the truss structure by using the equilibrium of its joints. If each joint in the structure is in equilibrium, then the whole structure will be in equilibrium. Using that concept only, at each joint we evaluate the forces, determine the forces in each member, and then take summation of fx is equal to 0 at that joint and summation of fy is equal to 0 at that joint. Considering the external forces acting on the joint, we can get the member forces, all the member forces that are connected to that joint. The same as be written here. At each joint, the member forces and any applied loads or reaction from a coplanar or co-current force system, which must satisfy two equilibrium equations: summation fx equals 0, summation fy is equal to 0, in order for the joint to be in equilibrium. These two equilibrium must be satisfied at each joint. Okay. So hope this point is clear to you. Now in trusses there is one more thing is that there are n number of members join to a trust. So there may be certain members in which there will be no compression or no tension. We call those members as zero force members. Now you people can see ask the question that what is the role of these members, and if they are not either taking any tension or compression. But for you, I will tell you, you please bear that in mind that these are not useless there. Actually, they have some other things to do. For example, it's not necessary for a member to transmit loads or to transfer loads to another members, but a member should be also present in a truss structure so as to maintain structural stability. As I already told you that if there is one member lacking in our truss structure, the truss can be unstable. So the biggest role of these zero form members is maintaining the internal stability of a truss structure rather than carrying any axial tension or axial compression. Other members which are occupied for carrying tension and compression are also maintaining the internal stability, but these zero force members are also necessary so as overall internal stability of this truss structure is maintained. So in a given truss structure, if a truss structure is given to you, so how you will be able to determine the zero force members? Because determining first of all zero force members is very necessary for the analysis of truss. When you determine the zero force members, then you omit all those members from this truss structure, that your truss structure get simplified, and you will be able to solve that truss structure very easily, either by method of section, method of joints, or method of sections. So the first and the foremost thing in the analysis of truss structure is, first you have to identify the zero force members, then take all those members away from that truss structure, simplify the truss structure, and then apply method of joints by writing the equilibrium equation at each joint, so that each joint is an equilibrium and the whole structure is also in equilibrium. So what is the what are the fundamentals behind zero force members identification of the zero force members is there are only two thumb rules you can use for identification of zero force members. One thumb rule is that if only two non-collinear members are connected to a joint that has no external loads or reactions applied to it, then the force in both the members is zero. Let me make you clear this thing with an example, because I think everything should be make made everything should be explained with the help of an example. Otherwise, it's very difficult for you people. Okay. So this will be supporting this structure here like this. Okay, like this. Let me draw one more member here. Draw one more member here, and draw one more member here. Okay, let me draw this. Let me draw this way. These are the members in this structure. Okay. Okay. So let me apply 10 kilonewton here and 10 kilonewton here. You people will be clearly able to see what are the reactions here. Here will be, this is joint A, this is joint B. It will be AY. This will come along AX, and this will come BX. So only BX. Okay. So this is along XY like this. So if I consider this joint, look at this joint, and remember M, that will be M1, M2. Consider this joint and this member M1, M2. Let me make it clear for you guys what we are taking. Take this joint only. Take this joint only, okay? Let's take this for you. Let's take this only. Sorry. Let's take this and paste here. Okay. Just look at this thing. Next, okay. So for this two members, M1, M2, I will write no force, no external force, no external force, no external force is acting. Both are non-collinear. So both are zero force members. Okay. Hope this is pretty clear to you guys. I made this explanation very simple for you.
Yes, sir, it's clear.
Hmm?
Clear, sir.
Yeah. So if at any joints two non-collinear members are joining and there is no external force acting at that point, you just, without thinking anything else, just take both of the members as zero force members. So now what you can do, if this was a question asked in examination like this, you just first at the top of the question you write M1 and M2 are zero force members. Force in force in, for example, force in, you will directly write F in force in M1 is equal to 0, force in M2 is equal to 0. Look how much question gets simplified using this concept. Then another type of zero force member identification is rule here. I have to make a new truss for that one. Okay, so let me do one thing. So we are having, for example, we are having this truss structure like this. It is having hinge here and it's having roller support here. Okay, so for example, I am having, let me draw one joint here. I am having one joint here. Okay, so I am having this member like this here, and I am having one more thing here. Okay, and I am having one more thing here, and other things will follow in this structure like this. So like this, for example, if it is joined by this type of, I made a very random truss. I don't know whether it's internally stable or not, because that's not the point right now. We are not checking internal stability, but we are determining the zero force members. For example, it's being acted by loads P1, P2, P3. Okay, so just check the reaction. It will be AX. Hope for you people this India, this not notations are very much understandable for you. It's so, since it is joint A, this is joint B, so AX is the reaction along X direction, AY is the reaction along Y direction, so it would be BY reaction along Y direction. And please bear that in mind. It's very good habit by drawing coordinate axes at each question, because from this it becomes clear to the examiner that what coordinate systems you are taking. So this X direction, this Y direction. So what the third point is, let me read it first, is that if three members, two of which are collinear, if three members, two of which are collinear, are connected to a joint that has no external loads or reactions applied to it, then the force in the member that is not collinear is zero. Okay, it's very two most important points. So maybe it will not be able, you will not be able to understand it from the text, but let's take a joint this one, this joint. Okay, so let M1, M2, and M3, and let's enlarge this joint and take this joint. Okay, okay, take this joint. At this joint, look, this is a joint here. M1, M2 are collinear. Okay, M3 is joined to them, and this joint has neither no external force, because P1, P2, and P3 are acting at different joints, and no reaction force. So at joint J, we are having two collinear members, three members joining, out of which two are collinear and one is non-collinear. And there is no external force, no reaction force. So what this rule says that there will be force in only M1 and M2, M3 will be zero force member. Okay. So let's take this. Let's erase this. Okay. So what we will write for this is M1, M2 collinear, M3 non-collinear. Okay, so what the rule says that one more thing is no external load, no reaction force. What the rule says that uh, M3 zero force number. So FM3 you will write 0. Hope this is clear to you guys. Okay, I made this explanation very simple for you. In the videos, you will not be able to see this type of lucid explanation for zero force members anywhere because I thought since this live session, instead of dealing with the numerical problems, it's better to explain the concept first, clearly explain. Then it's very easy to do the numerical problems. These two things are clear. Now I have you people have seen that with each concept I am trying to solve an example. Okay, so I have listed an example here. Identify all the zero force members in the Fink roof truss subjected to an unbalanced snow load at shown. This roof truss is known as Fink roof truss. Okay, so it's having loads at E, F, G, H points. Okay, and it is supported like this. So let's use the thumb rule for determining the zero force numbers. Let's consider the joint B. Okay, so at joint B, no external force, no external reaction. So this is collinear, this is collinear. So according to this force will be zero force number. Here the zero is written. Okay, very clear to you guys. Okay, so here are two. Now coming to this, this is collinear, this is collinear. Okay, so now we have to come from the other side. We have to come from the other side. Wait, yeah, we have to come from this side. This is collinear, this is collinear, so this will be zero force member. So when this is a zero force member, so just somehow imagine this is not there. Imagine this is not there. Okay, okay, you people got my point. So then there is this member. One more thing. Yeah, this is zero force member. This imagine this is not there. Okay. One more thing is that we have this is not a zero force member, this is not a zero force member. We have uh, three members here acting non-collinear, and there is no external force acting either. There is no external force acting at the joint. So this comes to be a zero force member, this comes to be a zero force member, and this comes to be a zero force member. Now this whole section, just imagine that this is not there, and this whole section is not there. We're having two members like here. I told you two members at which no external force acting. This will be zero force member, this will be zero force member. Look how easy it was able to compute uh, come calculate the zero force member. So look, this whole section gets deleted while analysis. We have to calculate forces in this class only. So this very easy exercise of determining the zero force members. Okay, I have created a mess here. Let me clean it. Okay, I hope you people will be able to solve this type of problems.
Sir, the NE members, I am little confused how it is zero force member because at joint E there is an external force, I think. So
We are
I'm a
considering,
little,
oh, we are very, we are considering any member to be, while considering it a zero force member, wait, we are considering joint N. So E member, there are force members, E, P, and EF. But while considering joint N, it satisfies zero force member properties. That's why any member comes to be a zero force member. Okay,
okay, sir.
is this clear to you?
Yes, sir.
So look, here it was collinear, these were collinear, one is non-collinear, this comes to be a zero force member. Okay, this is clear to you, this comes to be a zero force member.
Yes, sir.
Yeah, this is collinear, this is once deleting this member, there are again three members. This is collinear, this is collinear. Okay, This comes to be zero force member. Is this clear to you?
Yes, sir.
There is no external force. Then coming forward, this is this here this one. This and this. This is collinear. This is collinear. This non-collinear member will be zero force member. Deleting it. Okay. Is that clear to you?
Yes, sir.
Okay. So then this is collinear. This is collinear. This will be zero force member. This will be zero force member. Okay. Deleting all those which are zero force. These all are deleted here. Okay. Are you getting my point?
Yes, sir.
Now comes any member. Okay. Now look at this any member. Okay. Any member and CN member carefully. Okay. And take joint N and consider this example. If at any joint there is no reaction force, there is no external load. No reaction force, no external load. At joint N, both are satisfying. Both
Yes, sir.
NE will be zero and CN will be zero. You got my point?
Yes, sir. It's clear now.
Yeah, it's like this. You have to come from this side, and this side. Okay. So I think today I will not be able to touch numerical problem regarding this method of section. Maybe I will follow next section, or you can try it on your own. I have listed some examples for method of sections and method of joints. Sorry, and method of section. Maybe we will discuss in next lecture. Okay. So thank you so much for joining. I hope the doubts you people were having are cleared in this session. Anyway, if you have still any more doubts, you people are free to ask. I am here to answer your doubts. Hope whatever I taught you today is was clearly understandable for you guys. If you don't have any questions, you can leave.
Thank you, sir.
Okay, thank you.